Hello everyone, we are ImageDL. I'm Gladys and my teammate is Anu. Today we're going to talk about image demosaicing with deep learning. Image demosaicing is the reconstruction of a full resolution color image from an incomplete observation of a color filter array used in most digital image sensors in modern cameras. Traditional demosaicing algorithms can produce artifacts. CNNs have been applied to demosaicing successfully. Demosaicing entails converting a Bayer image shown on the left to an RGB image shown on the right. We experimented with various CNN models in the following two tasks: image demosaicing alone and joint demosaicing and super resolution. Super resolution is the recovery of high resolution images from low resolution ones. We used the CUV200 dataset, which includes 6,033 annotated color images of over 200 species of birds. We divided it into trained, validation, and test sets. Sample images from the dataset are shown here.
Our proposed model for demosaicing is as shown. It conceptually can be divided into three phases: color feature extraction, nonlinear mapping, and output reconstruction. We use larger convolution kernels in the earlier layers, which have shown to improve model performance. We also add a skip connection between the input and the final convolution map, which allows the model to reuse raw sensor values along with the features learned to perform rich feature-based reconstruction of the Bayer image into RGB image. During training, we use a multi-scale training approach in which the phase one of the model training is training the model at a low resolution input until the loss converges. In the second phase of training, we fine-tune the model at a higher resolution input. We found that this method improves our model performance compared to the model directly being trained on a higher resolution or a lower resolution.
For joint image demosaicing and super resolution, we implemented a modified version of the deep residual network proposed by Joe and colleagues as our baseline. It takes in a Bayer image input, passes it through a residual block-based network, and outputs a high-resolution color image. We then implemented RedNet20, which consisted of 10 convolution layers, followed by 10 deconvolution layers. A skip connection is present every 2 layers from the convolution layer to the mirrored deconvolution layer. Third, we implemented the super resolution CNN, which consisted of 3 convolutional layers. We then tried out a model where RedNet20 was appended at the end of the deep residual network, and another model where SRCNN instead was appended at the end of the deep residual network.
We use average peak signal to noise ratio as our primary metric for evaluation. The following table shows the different experimentations, and we found that the variable kernel skip connection model along with the multi-scale training achieves the near state-of-the-art performance of 39.6 PSNR. For the following are some visual results. We can notice that the model reconstructs the ground truth with an almost near perfection.
For joint image demosaicing and super resolution, the average PSNR are shown here. When the number of epochs was 3, SRCNN alone had the highest average PSNR of 30.4. When SRCNN was run for 10 epochs, the average PSNR further increased to 31.68. Example original and predicted images are shown here. In this example, RedNet20 alone produced images with the least visual artifacts.
Conclusion and future work. We achieved near state-of-the-art PSNR with our approach of fully convolutional neural network and multi-scale training approach. We plan to add super resolution to our demosaicing and multi-scale training approach. We also want to explore the possibility of joint image stitching and super resolution directly from raw Bayer data, which has many advantages in the field of high resolution photography and array camera systems. Thank you.